This is part 2 of the lecture for section 1.1. We're going to talk about how we can use matrices to represent linear systems. And essentially, matrices for linear systems are in the following two forms, either as a coefficient matrix or as an augmented matrix. So we have the following linear system. And the first thing we're going to do is write the coefficient matrix for this linear system. So we use a set of parentheses to define a matrix. Sometimes you'll also see matrices in square brackets. The way you generate the coefficient matrix is simply by taking the coefficients from the linear system, and you write that in each row and column of the corresponding linear system. So for example, for the first equation, we write the coefficients of the equation, which are 3, 2, and -1. The second row or equation is 3, 2, and +1. And the last equation, notice that there are no terms for x1 and x3. This simply means that the coefficients for those terms are zeros. When we write the augmented matrix for the linear system, notice that to the left, it essentially looks like we have the coefficient matrix, and then we write this bar, and to the right of the bar, we're going to write the constant terms, which are -2, 2, and 6. So the augmented matrix is the coefficient matrix augmented with the constant term. Notice that the size of the coefficient matrix is 3 rows and 3 columns, so we call it 3 by 3. The 3 rows represent the number of equations, and the 3 columns represent the number of unknowns. For example, column 1 represents the coefficients for the x1 term, column 2 for x2, and column 3 for x3. We're about to see how matrices can be manipulated to help us solve a linear system in a compact form. The way that we do this is by performing what's known as elementary row operations. You'll see these abbreviated as EROs. There are 3 different types of row operations. One is called row interchange, where we simply exchange any 2 rows in the matrix. One is called a row replacement, where we replace a row with the sum of itself and the multiple of another row. And the last is a row multiple, where we multiply a row by some non-zero scalar. So we're actually going to work on this linear system, and on the previous slide we wrote the augmented matrix for the linear system, and we're going to perform these row operations on the matrix to see how it is transformed. Now let's look at each of the elementary row operations. So first let's see how a row interchange is performed. So on the left here we have the augmented matrix for the linear system. And all we're going to do is, when we perform a row interchange, we're going to interchange 2 different rows of the matrix. So here we're interchanging row 2 with row 3. When we do that, we end up with this result. Below, I have the actual linear system. So notice that the result of interchanging the 2 rows of the matrix is the same thing as simply exchanging the location of the 2 equations. Notice that between the 2 matrices that we have, the 2 augmented matrices, there's a symbol here. This is an equivalence symbol. And in fact, what this equivalence symbol means is that these 2 matrices are row equivalent. They're not equal, they're certainly not the same matrix. Row equivalence essentially means that the matrices have the same solution set. And that makes sense, right? Because all we've done is exchange the location of the 2 equations, so certainly the solution set for this linear system, that is the one to the left, should be the same as the solution set for the system to the right. The next row operation we're going to perform is called a row replacement. In a row replacement, we simply take a row and we replace it with a multiple of another row. So here you see I've actually written out the row operation that we're going to perform. So we're going to take row 3 and we're going to replace it with a scalar, which is -1 times another row plus the row itself. So let's notice that I've just rewritten rows 1 and 2 because those will not be changed. And now we're going to perform this row operation. So row 3, we take negative 1, row 1, negative 1 times row 1 and add it to the element in row 3. So we have 3 plus a negative 3, which gives us a 0. Then we have 2, negative 2 plus 2, which gives us 0. And then we have a negative times a negative 1 plus 1, which gives us 2. And then we have a negative 1 times negative 2, which gives us positive 2, plus 2, which gives us 4. So now I've just taken this augmented matrix that we have here and rewritten the linear system from that, and we end up with the following new linear system. So notice that all this row replacement does, if we look at equation number 3 and equation number 1, is that we take equation number 3, which I have here, and do minus 1 times equation number 1, which I have here, and then we add those together, and that gives us the result that we have here. The last row operation that we're going to perform is a row multiple, which we see here. In a row multiple, you simply take a row and multiply it by some scalar. So we're going to take row number 3, which is given here, and we're going to multiply it by 1/2, and what we end up with is 0, 0. Of course, 2 multiplied by 1/2 is 1, and 4 multiplied by 1/2 is 2. So the linear system that results is the following. Notice that in this process we have solved for the variable x3, and I'm certain that given x3 that you can go back now and back solve to find the values for x1 and x2. And so I'm asking that in your reading assignment, please back solve this linear system, and write the solution to the linear system. You don't need to show the steps, just write the solution to the linear system in your reading assignment. So again, elementary row operations are performed on matrices, and they give us what we call row equivalent matrices when we perform these row operations. Row equivalence means that the matrices all have the same solution set. And as you could see, when we look at these different linear systems that result from these row operations, we haven't changed the linear system themselves. At least we haven't changed the solution. We've just altered the equations. So this process, we will see in the future how it is used to actually completely solve a linear system.